Moving on to the subject matter of super elevation. And to demonstrate basically what super elevation is, I want to go ahead and use something that you all are familiar with. This right here, remember this little noodle here, this is the plan view, this is the profile view. Well, on one side of this, I also have something kind of marked out in black. Hopefully you can see that's black. And that is the cross-sectional view. Now, to represent the cross-section of a roadway, I'm going to replace this with this right here. Okay, so on the roadway, your road is usually basically crowned, all right? So that crown is basically happening at the apex here, all right? And your roadway is sloped. And that slope is referred to as cross slopes, all right? So you have cross slopes that occur on your roadway, usually anywhere from about 1.5% to about 2.5% to allow drainage to occur from the crown all the way down to the subline layers or to the side where there's some drainage structures. Okay, so your roadway normally looks like this. Now, if I were to basically travel, if you were traveling into the board and you were traveling on a curve as well, let's just say the curve was right, or the road was turning right, basically your roadway would have to be eventually super elevated to adjust for that tendency for your vehicle to basically skid off to the side of the road. So your road starts like this, and in order to end up like this, it needs to basically go through a few stages. And those stages are tangent runout, where your roadway is pretty much at grade level, parallel to the ground. And then you have your continuous cross slope, where the cross slope down here, let's just say it was 1.5, is exactly the same cross slope at the top here of that roadway as curved. And then finally, super elevated. All right. So what I've done is pretty much exaggerated what goes on. Let me draw it as it exists. So let's just say you're starting here. You're starting at your road here, and your road is cross slope. All right, so it has this normal cross slope, and we're going in that direction. Okay, so we're basically curving here. All right, your roadway is curving. All right, so you have your cross slope here. At a certain distance from the cross slope that you see here, your roadway is going to basically do something like that. And we call that section right there the tangent runout. And then from that point on, you're going to have your roadway kind of curve some more. And we call this section here the continuous cross slope. Until finally, as you're traveling along that road, you are fully super elevated. Okay, so you have all of those things going on, and they happen in stages. Now, one thing that you may or may not notice on the road is that when you're traveling on a road that's basically has a normal cross slope, and as you're traveling on the road, especially as you're traveling into the curve, you don't automatically just go from here to full super elevation. That just doesn't happen. I mean, just picture yourself just going just from cross slope to a full super elevation. Your vehicle will most likely flip over, especially if you're going at high speeds, like I know some of you like to do. So we have to gradually go in stages fully super elevated. Also, we can't start the super elevation right at the beginning of the curve. In most cases, we start super elevating before the beginning of the curve. And what does that look like? Well, basically, let's just say, you know, you have your horizontal curve here, and you have your tangents, all right, that meet at a middle, which is what we know now as PI. Okay, so the tangents meet at the middle. You have your PC here, you have your PT there, and you have your roadway curving. Well, what I mentioned earlier is that you do not start super elevating your road right at PC. As a matter of fact, what happens is that super elevation starts a distance before PC. And that is what we need to figure out. Where do we start to super elevate, and where within the curve is the road fully super elevated and continues until it goes right back down to its normal cross slope. Okay, well, to determine that, you need to know two equations. Okay, and those two equations are called length of tangent runout and the length of runoff. Okay, now those equations are basically written as such. The length of tangent run out, which is also equal to L sub t, is equal to E in C over E sub D multiplied by L sub R. And your length of runoff, which is also noted as L sub R, is equal to W times N times E sub D. All of that divided by your delta, which is your relative gradient, and that multiplied by your adjustment factor. Now, before I get into defining each one of these things, I want you to notice something. This L sub R and this L sub R are the exact same thing. So you cannot figure out what your length of tangent runout is unless you know what your L sub R is first. Well, what does this look like on here? Well, your L sub R basically straddles PC. Okay, so it is the length that straddles PC. So L sub R starts about here and it ends about here. And the exact location I'll get into a little bit later. L sub t starts right where, or a certain distance before L sub R begins. So first you have your length of tangent runout, then you have your length of runoff, and then those combined lengths is the length required to take a road from a normal cross slope to a super elevation. So total length to change from a normal cross slope to full super elevation okay, is equal to your L sub t plus your L sub R. Okay, what does that look like in 3D? Well, if you can imagine, this is my 3D drawing here. L sub t basically is the distance required to change your cross slope from a normal cross slope, normal crown, to a length of tangent runout. So your L sub t is the distance from here to about here. And your L sub R is the distance from the tangent runout to a full super elevation. So your L sub R is the distance from here to here. Now it's weird because the only way you can figure out what your L sub R is, the only way you can figure out what your L sub T is if you know what this is. So you got to kind of work backwards. All right, well, what does that look like in the actual demonstration? Well, you can imagine this is my cross slope, and to go from from a normal cross slope to a length of tangent runout, basically L sub t, you're gradually going to increase your roadway on the left side here to this position. All right, so the length required to go from here to here is your L sub t. The length required to go from here to here is your L sub r. All right, one more time. Length required to go from a normal cross slope to a length of tangent runout, where one side is basically at a grade 0 or just level with the ground, that is L sub t. The length required to transition from an L sub t, where it's your length of tangent runout, to a fully super elevated road is L sub r. Well, the best way to understand something like this is to actually go through an example. But before I go through the example, I want to go ahead and define a couple more things here. So if you turn to your slides, you actually see something that looks like this. All right, so the length of superelevation runoff is as follows. These are the equations. And if you notice here, this equation has these terms defined for you. I got this out of something called the Green Book, which is published by the American Association of Safety and Traffic Highway Officials. It is pretty much what we call the Bible of Transportation and Highway Design. So all of these things are common to practice. So you have your width of one traffic lane, that's your W. Okay, and usually that's going to be 12, right? The number of lanes rotated, the number of lanes that you will be rotating to reach that super elevation. And then your E sub D is basically your super elevation that's represented in the percent. Okay. And you have your delta, which is your maximum relative gradient, and you have your adjustment factor for the number of lanes that you're going to be rotating. Well, these three terms right here you can pretty much figure out, or they can be given to you. But these two terms here have to be retrieved from a table. So let's look at this first one here, B sub W. That is the adjustment factor, okay? And if you notice, we're going to be working on this side because it says U.S. customary, and that's what we're used to working with, so that's what we're going to stick with. So if you have let's just say you're rotating 2 lanes, all right? So it's a 4-lane roadway, and you're rotating 2 lanes to get to the super elevation, full super elevation. Then your adjustment factor is going to be 0.75. So everything that you get here, you're going to be multiplying by 0.75. Okay, now these are in your notes. Now some of you may be wondering, well, what if my number of lanes that I'm rotating is more than 3.5? Well, that's what you have this equation right here for. And that equation is your adjustment factor that you can use for any circumstance, no matter what you may be designing for. So it is B sub W is equal to 1 plus 0.5, just in case you can't see it, multiplied by everything in this parentheses, which is the number of lanes. Alright, it's being rotated, minus 1. And all of that is going to be divided by the number of lanes. Okay, so you can use that. So if you have 4 lanes being rotated, you place 4 here, and you end up with your adjustment factor. Now, moving on to the relative gradient, that takes care of B sub W, adjustment factor. Let's move on to the relative gradient now. Now with the relative gradient, basically that gives you an indication of the rate at which you are changing the cross slope. Okay, and you can see here, again, we're working on this right side. It's really based on the speed that you're traveling. So the rate at which you're changing it is going to really depend on how fast you're traveling. Alright, so you notice here that, let's just say at the design speed of 15 miles per hour, for every let's just say 1 foot you move up, you are traveling 128 feet. Compare that to about 80 miles per hour design speed. For every 1 foot you're traveling up, you're moving 286 feet longitudinal. Okay, so that's pretty much the relative gradient, gives you an indication of how fast you are changing. All right, so both of those can be retrieved from tables, and everything else has to be given to you, or you can probably figure that out from other information that's given to you. All right, so that is the overall picture. And what we are going to do is we're going to be working through an example to figure out what our L sub t is and our L sub r is, and then we're going to add those two things together to determine what the total length to change from a normal cross slope to a fully super elevation, a road that's fully super elevating is. Okay, and if we know that length, then we can determine the station at which we should begin to super elevate. So let me go right back to that point there, because I mentioned that we don't just automatically go from a normal cross slope straight into super elevation. We begin a distance away from where the curve starts. Okay, and so that distance really depends on how much we're straddling, how much this length of runoff is straddling PC. Okay, now in practice it can range anywhere from 60 to 80% before PC, and anywhere from 40 to 20% after PC. Alright, so your L sub r, what we're going to be using in class is that our L sub r, once we figure out what that length is, we know that 70% of that length is going to occur before PC, and 30% of that length is going to be occurring after PC. Because remember, in class I said we're just going to take the average anytime there's a range. Okay, so knowing that, we can now move on to actually working through an example to get a better understanding.